So this is a common lab on the internet for microvoltaic cells. If you look that up, you'll see there's quite a few methods there. And what you basically do is you just quickly set up a mini lab with small amounts of materials and measure them like this. Usually you'll measure all of them, and you'll make a standard and measure them all against M1. Okay, but what I'm going to do is slightly different. I'm going to try and stuff you up quite a bit. So we're not going to measure everything. We're still going to keep M1 as the standard, but we're only going to measure it twice against M3 and M5. And we're not going to measure everything against M1. We're just going to do some random combinations with overlaps. And so if you did it in a rather erratic way, such as this, and you didn't always get it positive as well, so you just did them randomly like this, how would you solve it? And so I'm just trying to make a much harder question that means you'll be hopefully capable of solving anything. So I'm still going to make M1 the standard, just so that I can compare the results to make sure I'm correct. And so the first thing you're going to do, we'll just start with the first one. We'll analyze the first one. Okay, so having a look at the cathode and the anode. So we know which one's the cathode and the anode from the multimeter. And we can see the setup over here. We can see the SHE. So we know that for M1, this is what we're getting. And we know for M3, this is what we're getting from the diagrams there, and you're gonna just have to follow that through for 1, 2, 3, 4. So that being the case, we can add those up together, and so that's the actual equation that was happening. It gave us 0.83. Now, because we've made M1 the standard hydrogen electrode, we need to reverse this equation, and so we get M3 in this form, and so the reduction potential for M3 is right here. And so you can see that just makes life easy for you. So why wouldn't you do that all the time? So you can go down to number 4 and you can see the same thing going on there. It's just in the wrong direction. So we just reverse it so that we get this reduction potential for M5. So M3 and M5 are done. So what do you do about these missing gaps and wrong combinations? So you're going to use Hess's law. So for the M3, M2, if we write those according to the diagrams there, we can see that this is the combination that we're going to get. And so you can see you can cancel out the M3s here. And so you can rewrite it. So you get M2 just by itself as the standard. And you can see that it's 0.19. But again, you've got to get it into this form. So you need to reverse it. And there you go. So we got M2. And in the same way, you can you just copy off that pattern there. So you can add these two equations. So we're going to get M4 by itself, and then we're finished because M1 is 0. It's the standard. You can see the M2s will cancel out here. So we just have M1 and M4 by itself. It's, again, not in the right form. So we need it to be a reduction potential. So M4, and so we get minus 0.44. Okay, so just having a look at the answers then, you can see that we got the correct answers. Just for your interest also, these are what the actual metals were. And so why didn't we get, why are the numbers so much lower? There's a few limitations that you can think through.